Welcome. Today's tutorial will focus on using Mathcad. We'll cover some of the basics. We'll also cover some more complicated analysis that is very convenient to do, especially with uncertainty. So the motivation here is radiation principles. In particular, we're going to look at view factors. So the geometry that we'll consider is we have two parallel disks, and we want to calculate the view factor. So we have a set of equations here. We've got the radius of disk I and disk J. We normalize them by the L, which is the distance they are apart. That's capital RI and capital RJ, and was this intermediate equation S, which we then use in this view factor equation. And just as a little bit of background, view factor is it's something that varies from 0 to 1, and it's the amount of radiation leaving surface I that reaches surface J. So to some extent, it's the ability that surface I has to see surface J. And so if this factor is 0.5, that means 50% of whatever's leaving in terms of radiation surface I is going to arrive at surface J. Okay, so we'll learn how to code this up in Mathcad. In terms of functions, we'll also make some plots. So this is the graphical form of those equations. We'll go ahead and create these plots in Mathcad. In the process of doing all this, we'll be covering a lot of the basic tools that you need to do things in Mathcad. Okay, so this is the general Mathcad window. You'll see a red crosshair here. This is your cursor. You can move it around just by clicking different areas in the window. And wherever it is, as soon as you start typing, that's where your function or your variable is going to start being inserted. But before we get to that, let's just introduce the windows a little bit more. Each of these is a toolbar. You see two of them are selected, my evaluation toolbar and my calculus toolbar. They're currently located right here. This is my calculus toolbar, this is my evaluation toolbar. Within the evaluation toolbar, let's talk about this just for a minute. There's different ways of defining parameters. One is a numerical evaluation. The second one here is a definition. The third one is a global definition. You won't need to worry about that too much. I'll briefly introduce why you would care about it in just a minute. But the third one that you really care about is this symbolic evaluation. So the first two, there are numerical evaluation, then defining something, and then a symbolic evaluation. Everything we do will be one of those three. So just in terms of the definition, that's whenever we want to define a variable, such as I'll define a equals 5 here. And you see the shortcut. If you hover over this function, you can see a shortcut. So this is just the function name is definition. The shortcut to that is the colon. And so I don't need to type a colon equals. I can just type a, and then as soon as I hit colon, then it's going to automatically perform that shortcut function, just as we saw above. And so if I wanted to use this definition, again, it's a variable, it's a constant, it's equal to 5 in this case. If I wanted to use this in some other function, I could do a squared plus 4. And now I'm going to use just the simple equal sign to evaluate this numerically. I could type equals, or I could just punch this button, and it's going to give me the result as you see here, which is 5 squared plus 4 is 29. The way Mathcad works is whenever you are typing an equation in, or you're trying to evaluate something, it goes above that line to look for the definitions. So in this case, a is defined above it, and it's equal to 5. If I move this down, it's not going to recognize that. It gives me an error, right? It says this variable is undefined. So just be careful with that. Whenever you're defining something, using something else in a function, you have to define it above wherever you're trying to evaluate it. Okay, so that's a difference between a colon equals and an equal sign. One is evaluating it numerically, which is this one, and the colon equals is defining that variable. Okay, so we could also use this in a function. So we could make f as a function of a, and I'm going to define this function. So I have a colon equal, and let's say it's a cubed minus 5. So now if I get rid of this, and get rid of this, I could just type f of 5. And now, since I've defined f this function f, then I could just simply type the numerically evaluate equals sign, and it will give me the result. And now all I'd need to do, if I made a mistake here, all I'd have to do is fix my function. Maybe we wanted what we had before, and then it updates that line of code below. Okay, so that's kind of a brief overview of how functions work. What we're going to want to do is go back to our radiation equations. So let's make a function of capital R and then a different function of capital J. Actually, before I do that, let me talk a little bit about this cursor. So the cursor has a vertical and a horizontal blue highlight, just to let you know what section of the equation or what section of the text is currently being highlighted. So right now it's just the 2. So if I hit backspace, it's going to delete that 2. If I push the space bar, it's going to toggle how much I'm selecting. So if I hit the space bar once, it now is selecting the entire term a squared. Now if I hit backspace, it's going to delete that whole term instead of just the 2. And I could keep cycling through and hit backspace, and now it's going to delete the entire function. Right. So the way you toggle from selecting one area to the next increasingly larger area is the spacebar. So if I just keep hitting the spacebar, it's going to kind of toggle through these different options. The location of the vertical blue highlight line is going to change depending on when you push the insert button. So if I continue to push the insert button, you see that it's changing from the right side to the left side, and what that is indicating is the order in which the next function or the next command that you do is going to take place. So for instance, if I want to do x squared, I would type x and then hit shift 6 for my caret, and that's x squared. So you notice that when I did that, I had x typed and my blue vertical line was on the right side of my x, and so that means the next command that I do, which is the raise to the power command, is going to see x as the base and the next number as the exponent. So if I change that now, all I need to do is push the insert key, and if I push shift 6 again for my caret, it's going to recognize x as the exponent, and then the next value I input into my equation be the base. And so in this case it would be 2 raised to the x power. So this is a point of frustration oftentimes for new Mathcad users trying to figure out these blue lines, right? What do they mean? How do you control them? Because if you have a very complicated equation with multiple terms, numerators, denominators within numerators and denominators, you can try to just click and then hold the left mouse button down to click what you want to, but an easier way to do that is just between the space bar and the insert button. You can go just about anywhere. Okay, and the other way to move around the equation is the right and left arrows. Okay, so let's go back to our equation for parallel disks. Let's just do these first two for the time being, our dimensionless distance equations. So I'm going to type R, Ri, and the way that you get a subscript, you could come up here and type subscript like that, or you could just type the period command is the shortcut for that one. So Ri, and we're going to make this a function of, it's going to have 2 inputs. We're going to do little Ri, which is the actual radius of disk I, and the distance between them, which is L. So there's my function. I've told it what the input variables are, and now I'm going to use colon equals to define it, and it's just going to be the ratio of the 2. So it's going to be Ri divided by L. And notice when I did that, let me go back. So I typed R period. That's going to give me my subscript, and then I typed I, and then I just hit the division command and then L. And I'm going to do the same thing for capital Rj, and it's going to be a function of Rj and the same variable L, and this is simply Rj divided by L. Okay, so there's our two functions that we are going to look at first. Let me get rid of these. And the nice thing about Mathcad is you can move things around easily, but you can also just put some explanation as to what each line means. So, for instance, these, as soon as I start typing it still thinks it's a function. You see the blue lines, but it's now when I hit the space bar, it becomes text, and so it changes. This is no longer going to be seen as a variable. If I wouldn't have done that, it would have had a variable which was named these, THESE. So now it's just a comment in the Mathcad file. So these two equations are the dimensionless radii of disk I and j. And I could say C, Incropair and DeWitt textbook, table 13.2. So I mean, it's just a text box, so you can put anything in there that you want to. So now I have two equations. I could now plot. I could now just evaluate it. R of, let's say, 1 and 2. It's just the ratio. That's what we expect. It's 0.5. The other nice thing about Mathcad is you can do units. So if I wanted to define this as 1 meter and this as 2 meters, it's still going to be equal to 0.5 because it's dimensionless, right? So I'm taking a meter and dividing it by a meter. But if I wanted to put this one in inches, for instance, then it's going to automatically account for the fact that I'm meters in one case and inches in the other. And then if I leave one of these off, for instance, if I let L equal a unitless number 5, and R sub I is 1 meter, then the result is now going to be in meters because no longer am I getting rid of the units. So the units carry through, and it's a nice way to just double check you're doing everything right, because if your units aren't going to match, you're not going to be able to add terms together, for instance, and so on and so forth. So again, when I evaluated this, all I did is just like we did before, type the function and the inputs and then hit equals. So the nice thing that what I personally enjoy about Mathcad is the display. So what you see is what you get. When you're typing a complicated equation, it's going to end up looking just like it would when you write it on a piece of paper. So if I go back to here, let's look at the next equation that we're concerned with is this s. So let's make a new variable s, or new function s, and it's going to be equal to 1 plus, whoops. Now I'm going to make an error here on purpose, but we'll resolve it just a minute. So 1 plus 1 over rj squared. So I'm going to take that whole thing and square it. And now, if I hit the space bar, I can select different portions of what I have on the screen. So if I wanted to hit the division now, it's going to divide just the exponent. I don't want to do that. I hit the space bar, and now it selects the entire term, rj squared. So if I hit the division sign now, it's going to divide just that term. So I want to keep hitting the space bar until I'm ready for that equation, and the denominator here is going to be ri squared. Ri caret squared. Okay, so again, it looks just like it does on the screen here, on a piece of paper as you would write it. Some of the difficulties in MATLAB and Excel, for instance, is you have multiple parentheses, and for a very messy equation, it can be confusing as to whether you did it right or not. But here, it's exactly as it would appear on the paper. So the reason why I'm getting a variable here is the fact that I haven't defined this as a function. I'm just trying to. So if I would have had ri equals 5 and rj equals 2, then I have no problem. There's no issues down here. And you notice that these two lines are slightly below the function lines that I just made earlier. So what this does is it says I need to find an ri and an rj. It goes until it finds it, and then it comes back and evaluates it. If I change the order of this, then I get the error again, because this is saying, well, hey, this is a function, and you haven't told me what the inputs to that function are. And so you can kind of redefine variables from one line to the next just by doing as I've done here. So what we want to do here is we want to make s also a function of ri and L and rj. Right, so it's going to be, there's going to have 3 inputs. I could do this 2 ways. I'll do it one way and then I'll do it the next way. Rj and L, close the parentheses, and now I've got to make this Rj of little rj, whoops, and L, and then I've got to tell this is a function as well, so this is going to be R sub I and L, and now there's no issues at all. So now I could evaluate this if I have R as 1 meter, Rj is 1 meter, and L is maybe 0.2 meters. It's going to give me a value for S. Right, and it's dimensionless as we would expect it to be. The other way we could do this is just since we could maybe calculate these beforehand, and we could make S just a function of capital Ri and capital Rj. Since within the S equation there's no little r and little or L. It's just it's incorporated into there by the fact that our big Ri and big Rj are using those inputs, but we don't necessarily need to use that. So we could write the equation like we had before, and now we don't need to say it's a function because we said that these variables are now inputs into our S function. So again, now we have an error here because I have 3 inputs, and it says that you only need 2 inputs because this line is slightly below this line, so it only goes up to here. It doesn't even recognize that that one's there. And so I would want to type S of let's see what it is. Well, 2 and 2, let's say. Okay, so we can evaluate it. We can go one of 2 ways with this. In fact, let's do this route. So we could first calculate these, and then let's get rid of this, and then we'll redefine them. I'm going to move these down a bit and type the input variables to this problem are the radii of the disks and the distance apart. So let's define Ri as 1 meter. Let's do Rj as 1 meter and L as 0.2 meters. Okay, so we have our input variables. That didn't change anything that's going on here. It's going to cause us problems down between here and there when we start to do partial derivatives, but the way we're going to handle that is just redefine this as Ri. And now, since we've kind of hard-coded these values above, we don't need to call these functions. And what I'm going to do now is just I'm defining this, but I can also, since these variables are defined above, I can also go ahead and evaluate that on the same line just by hitting anywhere and typing the equals button. So we're defining it as Ri over L, and then we're evaluating that numerically to see what it equals. Okay, so we have our equations set so far. Now we just need to get the final equation for our view factor, and we can do this one of 2 ways. We can redefine S, kind of like we did with these, and let it equal some constant, or we could make this Fij a function of all these different variables, right? So it's a function of S. We could just take this definition and put it in there. And then it's just a function of capital Ri, capital J, little rj, and little rj. Or we could just leave it as S as a function of those 2. And I think we'll do the latter. So let's type Fij, and I'm going to make this a function of Ri and Rj only. And the way that I'm going to do that is just type it just like we see here. We've got S, and since I haven't redefined S, I've got to make this a function of these different variables, Ri and Rj, minus the same thing. So I'm going to hit the space bar till I have this whole term selected. Then I'll hit Control C for copy, Control paste for there. Don't worry about your error yet. This is going to be squared, I believe. This is S squared. and then minus, whoops, so I needed to push spacebar. There we go. Minus 4 times. So look at this quotient, this ratio here, little rj over little ri. And if you go to the definition of the dimensionless radius here, you're just normalizing by L. So rj over ri is the same thing as capital rj over capital Ri. And so instead of making this a function of big R, both big R's and both little r's, I can make this just a function of the dimensionless forms of these. And that's going to be squared. And then this quantity up till here is going to be square root of that. Okay, so our function's ready to go. Now we can just simply type in Fij. Notice we got 5 and 5 here, so I could just type 5 and 5. Or since I've already defined Ri and Rj, I could just leave it as this and get the same number. Right? But again, if I get rid of these two lines, it's going to give me an error. Why? Because it no longer recognizes those as a constant. It's still saying the first time I see those two, these are functions, and this isn't going to work. Okay, so that's kind of the basics on how to create functions. We could now go to this plot that you see here. Let's go ahead and plot this, and then we'll do a little uncertainty. So we have our function. Let me get rid of these. This is our master function here. So really, all we need, we could get rid of everything that you see here and still be okay. Why? Because we don't need to define Ri and Rj necessarily yet. We could just have the one equation for S and the next equation for our view factor. Okay, so this is our equations. Now we can go make a plot. And the way that we're going to do that, oh, actually I've got an error here, don't I? I didn't square these yet. So according to our equation, this is Rj squared and Ri squared. Okay, so the way we insert a plot, we go insert graph xy plot, and you notice to the right here is the @ symbol. That's again the shortcut. So we could either go ahead and select that through the menu, or we could just type the @ symbol, which is Shift 2, and you see we get our plot. We can resize it. We haven't told it what to plot yet, but we can move it around and resize it as needed. So now we come to the y-axis and say, well, we're gonna plot f of, let's go to the plot here. So this is f on the y-axis. Each of these curves represents a different capital Rj, and the x-axis is capital Ri, not capital Ri, but capital Ri inverted, right? So this is r divided by L. So in the x-axis, we're going to type 1 over Ri, and we're going to plot the Fij of Ri, which we're going to let vary. And then let's choose one of these curves, maybe capital Rj equals 2. And let's plot that. And you see that by default it's going to choose some range of my x variable. It doesn't make sense to have a negative number, so we're going to go ahead and actually let's go back to the graph. Here you see that it's actually log scale, so we're going to go from 0.1 to 10, and we're going to go ahead and make that a log scale here in just a minute. So this is what the plot looks like for the regular scale. So we can double click here, either on the axis. If we do it on the axis, we can just select log scale like that. We could also just double click on the graph, and we have a number of options available to us. If we wanted to take the x-axis and make it log, we could do the same thing with the y-axis if we wanted to. We're not going to do that, but so here's a plot. Here's Ri equals 2. That looks pretty reasonable. It kind of goes up to about 0.8, and that's where it cuts off here. So I'm going to change the range of my y-axis to start exactly at 0, and then go up to 1, because we know the view factor is never going to be greater than 1. Right, so I could just copy, and the way that you input a second plot on here is the comma. Gives you another one. I apologize because I only know the shortcut for this one. I'm sure there's a way to get the other equation in there. and now I can just go in here and select a different curve that I wanted to look at. So 5, for instance. Here's the 5, and it's all looking very, very reasonable. All right, let's do one more up to 8. Okay, so we could create this entire family of curves with multiple plots. And the way that, if you double click here, you've got these options up here. Here's things to do with the axes, the traces. That's what it's referring to when it says these are the lines. Different curves or different traces. We could change the labels. So this is capital RJ equals 2, our first one. Our next one would be capital RJ equals 5, and our third one that we have there is RJ equals 8. And at the bottom of this, right now the hide legend option is selected, meaning it's not going to give us a legend. So let's deselect that, and we could have it be below the graph, but we've got plenty of room here in the bottom right hand corner, so let's just tell it to go there. We can hit apply and just make sure it looks like we want it to. Another thing we can do is hide the arguments, which by the arguments it means what you've selected to put in here. So notice, let's not select that. If I hit OK, then my plots, my labels are not there, right? The labels are essentially what I've told Mathcad to plot. But if I come back here and I tell it to hide the arguments, then those are going to disappear once I deselect that plot. And then I can come in here and next to traces, number format, the labels, I can give it an X label. So this is Ri raised to the -1 power. My y-axis is my Fij. And so now I deselect it. I've got more of a presentable plot here. Okay, so that's kind of a brief overview on how to do functions, how to create plots, how to work in the Mathcad environment. Okay, so next, now let's move on to uncertainty. Let's scoot this down a little bit. And for the uncertainty, we're going to let's use these equations, since now we've only got 2 variables to work with. We could take at the beginning we're going to have 3 variables: the radius of each disk, 1 and 2 variables, and then the distance between them. There's our 3rd variable. Each of those variables are going to have some uncertainty associated with them, and the question is, how do those propagate through to have the uncertainty in our view factor? So we could calculate a view factor based on all these measurements, but then how do we determine what the uncertainty in that calculation is? So presumably we're going to be given uncertainties for each of these 3 variables. Let's assume for a minute that we understand how to do that, and we come up with uncertainty in our dimensionless radius. So now we have the uncertainty of R1. Actually, let's go ahead and do that. Let's put some additional lines of code in here. The ones that we deleted earlier, right? So here's our capital R. This is a function of Ri, and L is going to be just the ratio of the 2. And let's do the same one for Rj. One nice feature in Mathcad is you can, if you want to look a little nicer and clean it up, you can select these 2, and then here's the alignment tools if you want to line across or up and down. So I'll do this just to make them kind of look a little better. This is going to be my Rj equation. So here's our equations again. The way that we do uncertainty is to take the partial of this with respect to each variable. So let's take Ri. This is going to be, again, determined from 2 inputs that we measure independent, which is the radius of disk I and the distance from I to j. And we're going to go to our toolbar for calculus here, and let's do a derivative. We could type the derivative of this function with respect to Ri, and notice we haven't defined any numerical values for little Ri and or Rj or L at this time. So we could try to type equals, and that's going to give us a problem. This is a situation where you'd want to look at the symbolic evaluation. And so you see that the derivative of that function with respect to Ri is just going to be 1 over L, and that makes sense, right? So all we would do to change the change what we're taking the partial with respect to is just change this factor here, and then we get the partial with respect to L. So this is what you use in uncertainty analysis, because we need to know how many ever input variables we have. We need to take the partial with respect to each one of those independently, and this can get very hairy, again depending on how many input variables you have. So as you recall from uncertainty, so let's define uncertainty of Ri. This is going to be the partial of this with respect to Ri times the uncertainty in Ri squared. And we're going to do the same thing. We have two terms, and now we're going to do it with, I need to do this. I need to change this back to Ri. So now we've got the partial of this with respect to Ri times the uncertainty of Ri. We're going to take that quantity and square it, and then we're going to do the same thing with respect to our L. And we're going to square that, and we'll take the square root. So take all this and raise it to the 0.5 power. So it's giving me a red because I haven't defined what Ri is. I could make this a function of Ri, Rj, and L, and that would get rid of all these. Well, my uncertainty, I forgot my uncertainty, didn't I? I could also make it a function of that uncertainty, right? Of Ri and a function of the uncertainty for L. So now all my red has gone away, and Mathcad is able to make calculations with this function. But I don't want to get too carried away with the inputs, and so what I'm going to do is just define this. Let's give some constants up here. Ri is this, Rj, let's let it equal 1 meter, and let's let L equal 0.2 meters. So notice what's happened here is the symbolic evaluation that we had before was negative Ri over L squared. And what it's done is it's taken that, and it's still evaluating this properly, but it's saying, hey, I found actual constants for these variables up above, so I'm going to go ahead and put those in there. So if we took Ri divided by L squared, we're going to get 0.25. We got meters on the top, we got meters squared on the bottom, so it's going to have units of 1 over meters. So that's what we get. We get the negative because of taking the partial, right? So now since we've defined those, let's go ahead and define the uncertainties in each of these. Let's make this maybe a 2%. So a 2% uncertainty would be 0.02 times Ri. The uncertainty in Rj is, let's make it 2% as well. And there we go. Actually, let's do this for L as well. The uncertainty L, let's make this 5%. So now I can go ahead and get rid of all these inputs because I've now defined them, and no longer do I have the issue of having the errors here. And I've defined this URI, and I can also give it a numerical value because again I've given the proper values above. So the uncertainty in Ri is equal to 0.269. So let's evaluate that. Let's see what that means. That means the value for Ri, substituting these values in, is going to be 5. So that means I'm going to calculate a value of 5, and the uncertainty in that, due to the uncertainty in my measurement for my radius and the uncertainty with my measurement for this separation distance being 2% and 5% respectively, then it's going to be 5 plus or minus 0.269. So in terms of percentage, if we wanted to take that uncertainty of Ri and divide it by the value for that, that's going to tell us the percent uncertainty. And this is a little over 5%, which makes sense because we had L, which had a 5% error, we had Ri, which had a 2% error. In terms of percentage of the overall result, you know, it makes sense that we're propagating through, it's getting larger, and so on and so forth. So we're going to apply these same concepts now to the S equation. And what I'm going to do is now just start with an uncertainty in Ri, capital Ri's, I'm just going to let it equal about 5% of Ri. And we haven't defined Ri, so let's go ahead and define Ri up here. Equals 5. Rj equals 5 as well. I didn't make this a subscript, and then it gave me problems. So now we've got, we could very well delete all of this and still be okay, because we've redefined this Ri and Rj. No longer are they functions as we had up above. I'm just go ahead and I'm defining them as constant values. So let's let the uncertainty of Rj just equal the same thing. So let's let that equal the uncertainty of Ri. And again, we've defined them, but they're all constants, so we could go ahead and numerically evaluate those as well. Okay. Now I can take my function s. Actually, I don't care about s so much as I care about this view factor, this Fij. So we could apply the same concepts that we're doing up here to our uncertainty for Fij, and let that equal. I'm just going to go ahead and copy this down. But we'll need to change the parameters, obviously. So this is function Fij, and it is a function of capital R I and capital Rj. And then we have the uncertainty. In this case, it's going to be the uncertainty of Ri. And we're going to take the derivative of this with respect to capital Ri. Don't want to evaluate it yet, but now we've got this term, and we've got a second term, which again, it's only a function of two variables, so we're going to go ahead and make this j and give us the uncertainty of j. Take that, take the square root of it, and we get some value, and that's equal to 0.058. So again, that's the uncertainty in the view factor. We need to evaluate our view factor, and it is 0.819. So what, in other words, what this is our view factor is equal to 0.819 plus or minus 0.058. Okay, so I kind of did this in two steps. You could do it all the way from the beginning and kind of see how it propagates all the way through. This is now no longer giving us the graphs. Why? Because we went ahead and defined this Ri as a single value. No longer is it recognizing it as something I can take this as a function of. So all I got to do is call this a dummy variable, call this Ri2, and then come down here, change it to Ri2, and we get what we had before. Okay, so we had r's equal to 5. Let's put another curve in here. Oh, we got the 5 curve. So the 5 curve is this blue dashed line. So we've got 5 and 5. So if we come over here, we could right click and trace. Let's go on this curve. Let's move this up a little bit. And we come over until our x value is equal to 5, because this is the, so this gives us a y value of approximately 0.96, which does not agree with what we're getting for the view factor. So let's see if we can figure this out. So our x value is 5, our r value, both our r values are 5, yet it's telling us it's 0.89 here, but this is 0.96 there. Okay, so the whole reason why is because we're not plotting r on this x-axis, we're talking 1 over that. So instead of going to 5, we need to go to 1 over 5, which would be 0.2. So we go to 0.2 for our x value. So we're pretty close to 2 there, and we go on the curve which represents our j of 5, and we see that the y value, which is our f view factor, is 0.84. So this makes sense now. Okay, so this could become very complicated. This could easily you could easily type this equation in. It's a function of two variables, this x bar and y bar, as is this. And you could, without having to calculate or compute by hand these partial derivatives, you could very easily do them in Mathcad. Okay, so this concludes the short tutorial for Mathcad, and you're welcome to use this in your project. Just keep in mind that what you don't want to hand in is a bunch of equations. You need to talk your reader through, such as I tried to do in the beginning. We could say these are the the following are the known constants for this problem. And make sure you talk your reader through your analysis. Don't just have a bunch of equations. And use the align tools here to make it more presentable. You can also just take something like this, copy it, and go into Microsoft Word and paste it, and it'll appear as an object, which is a little easier to do than the equation editor in some instances. But okay, so hope this helps, and good luck.